One more time. Homework due tonight. Test. Posted tonight, due next week, but the last day to work on anything is the last day of class, the 21st. So before we do practice problems, I want to go over definitions and do examples, and then I have like worksheets that we'll do together. So back to some notes where we talked about a walk. So it's a sequence of vertices where you go from one vertex to the next through an edge. I'm just going to put sequence of vertices. Okay, and a path is a walk, but also you use each edge one time. It's okay to use a vertex more than once, but an edge has to be used only once. So again, walk is kind of loose. You can go back and forth over an edge if you want to. A path is more restricted. You can go over an edge only one time. And a circuit is a walk and a path, and you start where you end. So it's a sequence of vertices. You cannot reuse an edge. And with a circuit, you start where you end. And then the practice for today is for Euler paths and Euler circuits. So before we go there, an Euler path is a path where you use each edge one time and you use all edges. An Euler circuit is a circuit where you use each edge once, you start where you end, and you use all edges. So the path part, use each edge one time. Don't reuse an edge. Okay. But an Euler path means you use every edge. An Euler circuit means don't reuse edges. Start where you end. And with the Euler part, it means use all of the edges. Don't do this, and also do that. So I would like to do examples first, and then we're going to go into using some theorems. So example for Euler path. We're going to have a graph that starts with the vertex at top, goes down and down and down, over and back to that vertex right there. We're going to call this vertex A, B, C, D, E. So for Euler path, we need to use each edge one time and use every single edge. I'm going to just start at A and go down to B and down to C and down to D. So my sequence looks like A goes to B, goes to C, goes to D. Then from D, I'm going to go to E, and I need to cover every edge, so let's go over here to C, and that's going to be good. Okay, A, B, C, D, E, C. So I want to point out that I reused that vertex C. It shows up here and it shows up here, but that's okay. I can revisit a vertex. I just can't go over the same edge more than one time. And I was able to get through every single edge, so I got my Euler path. Okay, let's draw another graph. Okay, this time we want to find an Euler circuit, and the graph looks like, let's see, we've got I think I can do this. There's maybe just a square shape like this. And I'm going to put a vertex right here. Go over that. And connect. No, it's not good. Let's do connection. Okay, I think we can do this one. We're going to label it with, let's go RSTUV. So we're going to pick a place to start. And then we want to end at that same place. I might try starting at R. Or the corner, just pick R. Here we go. Okay, so for circuit, we need to start where we end, use every edge once, and for the Euler circuit, use all edges. I go from R, let's send that to S. And then from S, let's take care of going over to T. And let's get from T to U. I think I would like to go through this triangle shape. So let's go from U to S and S to W. Let's go back down to U and then over to V. Okay, and then we can get the rest of the edges by going to W and then to R. And luckily we started at R and we've ended at R, so we got that. W and back to R. So use each edge one time. I got through all of the edges and I start where I end. So before we move on, I just want to remind you that even if this sequence has a starting place that's the same as the ending place, you need to also check that you don't reuse edges. And if it's an Euler circuit, you also need all of the edges. Okay, but you won't actually have to find a example on your test. You can use the theorems. So let's write what those theorems are. Just like the shorthand version. For an Euler path, if you check the degree of the vertices and there's 2 odd, then you have an Euler path. For an Euler circuit, you check the degree of all of the vertices, and if everything is even, or if there's no odds, then you know that somewhere in your graph you can find an Euler circuit. So odd. And so if you find more than 2 odd vertices, you can't have an Euler path, which means you also can't have an Euler circuit. Okay, so I've got some practice problems that we're going to do together. Let's get this ready. And you can go ahead and try to draw each graph, but it might, I don't mean to, since I have them already ready in Paint, I'm just gonna go ahead and talk through the problem. If you want to draw the graphs for your notes, you can. I'm also going to post my work though to this week's module. So I'm going to post all of these graphs with all of the notes on them on Canvas. Okay. We're going to start with this. Okay, sharing the screen, and here we go. Okay, so you should see a Paint program picture. Let's see, where are my comments? If someone could tell me in the chat, can you see these graphs that I've got posted? It's about finding Euler circuits and Euler paths. Yes, thank you. Okay. So for each of the following graphs, we're going to find out if it has an Euler circuit, Euler path, or neither. Which means we're going to use the theorems and go ahead and check the degree of all of the vertices. If we find 2 odds, we've got an Euler path. If there's no odds, Euler circuit. But as soon as I get more than 2 odds, it's going to be neither. Cool. So just going to the first graph, get every degree of every vertex, or at least get started on finding the degree. So degree 2 has 2 connections. This is degree 3 with 3 connections coming off of the vertex. Degree 3, degree 2. So if I get one more odd, which I have right here, this is degree 3, I could go ahead and stop and say that's going to be neither. So when you have more than 2 odd vertices, like we do right here, there's not an Euler path or Euler circuit. Euler, oh, it's not an Euler path or circuit, it's neither. Let's go to the next graph, check every degree of every vertex. This would be degree 2. And move over here to degree 1, 2, 3, 4. This is degree 2. And degree 3. Degree 2. Degree 3. Okay, in this graph, I've got 2 odd vertices. They're on the top, which means there's an Euler path. All right, next one is on the side with the top vertex having degree 2. Let's go down here. This guy is 1, 2, 3, 4. Degree 4. Degree 2. And 3. This degree is also 3. So it happened again where I've got 2 odd vertices, which means I could find an Euler path in this graph. Yes, okay, cool. Okay. So this is the graph that I drew earlier, and we found an Euler path. But this time we're going to use the theorem. Degree 1, degree 2, degree 3, degree 2, and degree 3. Oh, wait, just 1, 2, 3, 2, 3. Okay. I did it again, it's 2. 2 connections makes it degree 2. Okay, this one also has 2 odd vertices, so Euler path. Oh, okay, it's good enough. And over to the next graph. We have a degree 3 and another one. Top is also degree 3. And the middle is degree 3. So these ones are all odd. Or when you have more than 2 odds, it's neither. Okay. Next graph. Check in the degree. 2 on the corners. Okay, 2, 2, 2, 2. This is degree 3. This one, let's check with color. So there's 1 connection, 2 connections. This is going to be 3. That's 4. And 5. And 6. And the last one here is degree 3. Okay, looking at all the degrees, there's 2 odd, which means it could find an Euler path. All right. Next group of graphs is going to have this graph on the far left. Start labeling the vertices with their degree. Getting every corner with just degree 2. Like all of the ones on the edges here, the sides. Okay. Let's carefully check these other vertices. This one's degree 1, 2, 3, 4, 5, 6. And here's degree 1, 2, 3, 4. All right. Looking at all of the degrees, this time is the first time that they're all even. And when every degree is even, you can find an Euler circuit. Which is going to have also an Euler path, but an Euler circuit is stronger, so go with the best definition, or like the best possible choice. Cool. With this graph, let's get the easy parts where you have degree 2. This one's degree 2. Up here in the middle is degree 2. And also this one too. Cool. This has degree 4. It's 1, 2, 3, 4. 1, 2, 3, 4. And same on the other side. 1, 2, 3. All right, all of the vertices are even. So we can find an Euler circuit. Over on the side, there's a degree 2 on this bottom corner and the top corner. Let's get that corner. Degree 2, degree 2. Degree 4 is the next one. This is degree 3, the bottom middle. The very middle is degree 4. Let's go to the side. They're all even still, so I'm going to keep checking. 1, 2, 3, 4. And 1, 2, 3. Wait, 1, 2, 3, 4, 5. Oh, okay. I see. This one's an odd one, and the bottom middle was odd as well. So I don't have an Euler circuit, but I do have an Euler path. Actually, I'm going to take away the red squares because they're a bit distracting. Let's do circles. Okay. Oh no. There we go. This one has an Euler path, and we've got 2 more. So going from left to right, let's check the degree of all the vertices. Degree 2, degree 2. This degree is, actually let's go up here to degree 2. And then this one's a 4. There. Okay, this one's also a 4. And a 2. Okay, this corner is degree 2. Degree 4. Degree 4. And over here is a 2. This one's degree 4. And 4. And 2. Let's go back up to the top and get this degree 2. Degree 4. And that's got 4 connections. This one's got 2. Almost done. Degree 2 and degree 2. Okay, so I want to double check before I say anything. Yep, they're all even this time. So when it's all even, you can find an Euler circuit. Last one. for this worksheet, we're checking degrees of vertices. Let's go with degree 2. This one's degree 3. And I'm going to go here. Here's a degree 3. So if I find one more degree 3, I'm going to stop. Because once you have more than 2 odds, you can't find a path or circuit, an Euler path or Euler circuit. So let's go right here. There's one right here where it's degree 3. So I can stop and say there's more than 2 odd vertices. So we can't find an Euler path or Euler circuit. So I'm going to be posting this work to Canvas. It will be on this week's module. And we're going to do another one. So the next one will help you with your homework problems, and I'll have more of them next week when we do review for exam 3. Okay, so you should see a new paint program, and it starts out with talking about neighborhoods are laid out like a grid, like the ones below. So again, if I could get someone in the chat to say, yes, I can see the screen. That way, just cool, thank you. So let's go ahead and check this out. Neighborhoods are laid out like a grid. There are some examples below. Is it possible for a mail carrier to walk down every street once, I should say only once, I get that, only once, and return to the place that they started? So if I need to cover every street, I need an Euler path or Euler circuit. If I need to start where I end, that means I'm looking for an Euler circuit. So we'll put that to the side. Okay, and use, like we visit every street, okay, and we want to go down each street one time, and we want to start where we end. So looking for an Euler circuit. So these are just kind of like scratch work ideas on the side, but we have to actually check the degree of the vertices of the graph. Let's do that. Let's go with degree 2. And 1, 2, 3, 4 is going to be next. Degree 3. Okay, so I could stop right here. An Euler circuit cannot have any odd vertices. So it's not all even. So it means there is not an Euler circuit. Okay. So the answer would be no, they cannot do that. see. Just kind of fill it out. So you can't visit every street one time and start where you end where you start. End where you start. A side question would be, could the mail carrier visit every street, but it doesn't matter if they start where they end? So that would be looking for an Euler path. So if they could be dropped off somewhere and just go along every street and be picked up wherever they were done, that would be looking for an Euler path. I think we'll save that idea for next week when we review. Okay, so in this one, we're also looking for an Euler circuit. We want to go down every street, make sure we do each street one time, and start where we end. Which means we want an Euler circuit. Cool. Okay, so let's look at the degree of a vertex. This one's degree 2. Actually, going over here to degree 4. Degree 1, 2, 3, 4. Let's get in here. Oh. Okay. Just want to focus on the graph. Thanks for being patient. Cool. Moving on to degree 2. And 2. Degree 1, 2, 3, 4. And it's degree 4. This corner is degree 2. Degree 4. And this one also. Okay, here we are at degree 1, 2, 3, 4. Degree 4. All right. Oh, right there. And we're at the bottom 2. Each has degree 2. Cool. So I've checked all of the vertices. They all have even degree, which means I could find an Euler circuit. So it is possible for a mail carrier to start somewhere, go down each street one time, visit all of the streets, and end at the same place. End where you start, I guess is a better way to say it. So I'm just thinking, if on your test you say that it is or isn't possible because an Euler circuit does or does not exist, that's enough of a statement. But so like we'll practice responses next week when we review. But I just wanted to fully explain like what the question's asking and what we're looking for and how we can find it. So our first map, you could not find an Euler circuit, so you could not make that trip that we're talking about. In the second graph, you can do all of those required things. You can find an Euler circuit. Okay, so we're going to save this work. It will be posted to Canvas in the module for week 14, next week's review week, and then we're in week 16, which is finals week, which for us is just a makeup week. So if you weren't here earlier in class, if there's anything you want to work on, the very last day to turn something in is the 21st. Okay, so, and before you go, in my last class, we talked about how there's no scheduled Zoom meetings for next week, but we do meet next week. So I'm going to check my settings, and if I can have those meetings stay posted. If they disappear, then I'll send out an email with the meeting info. It's on the syllabus. I was going to try to paste it on the chat, but I'm just trying to say we do meet next week on Tuesday and Thursday to review. Okay, that's it for today. Thank you for coming to class. Also, I really appreciate the work we've done together this semester online. It was tricky. I had difficulties, but you guys were great. So we're going to wrap it up next week. Bye, everyone. Have an awesome weekend. Thank you. Yeah, thank you too. Okay.